Now we're going to see the elliptic cone. The elliptic cone is a cone made of ellipses. This is x squared divided by a squared plus y squared divided by b squared equals c squared divided by c. So if you do horizontal cross sections like this, you have in the cut or in the surface that you would see would be ellipse. So if c is equal to 0, you have x squared divided by a squared plus y squared divided by b squared equals 0. This was, because I put 0, exactly in c equals 0, that is exactly in the xy plane, you have 0, 0, 0, that is, you are just crossing that point, the origin, because there is no two numbers that when you square them and you add them, you have 0, unless both of them are 0. But if you put a, let's say, parallel plane to the xy plane, so c equals c naught instead of 0, here you will have c naught squared divided by c, and this is just a number, and so you have a ellipse. So when you do cross sections, you have ellipse, where this, the distance from this center to a vertex, this vertex, that is this black line, bold black line, that's B, and from here to the other vertex, that's A. So we have these semi-axes in the ellipse. Next is, now if you do a vertical cross section, let's say in the YC plane, that is when x is equal to 0, that is in the plane x equals 0, you have y squared divided by b squared equals c squared divided by c. So you have, let's solve for c. So you have c equals c divided by b, sorry, c squared equals c squared divided by b squared times square y. You took the root and you have c equals plus or minus c divided by b y squared. So when you do cross sections in the YC plane, you only have these lines. No matter where you do the cross section, you only have these lines. Next, if you now do a cross section in the y equals 0 plane, so it would be in the xc plane, you have a square x divided by square a plus 0 equals square c divided by square c. And so you have, solving for c, you have x squared divided by square a times c equals c squared. You took the root, and now you have c is equal to plus or minus c squared, c over a times x. So now you will see these black lines in these thin black lines. So when you do horizontal crosses, you have ellipses, except in the origin, and when you do vertical cross sections, could be in the YC plane or in the XC plane, you have lines. This elliptic cone is symmetric in the three axes. Here is symmetric, here and here. Here is symmetric, this part is symmetric with this part, and here this part is symmetric with this part. And so this is a elliptic cone that in 3 dimensions, you see it like this here, and like this, another like this. So this is the elliptic cone. The interesting thing is that I don't know if you already see the video or if you are going to see the video, depending on which one was first, but the hyperboloid of one sheet and the hyperboloid of two sheets, both are asymptotic to the elliptic cone. This is the equation of the hyperboloid of one sheet is x minus x square x divided by square I plus y squared divided by square b minus square c divided by c squared equals 1. And the hyperboloid of two sheets, we have minus square x divided by square I plus, minus square y divided by square b plus square c divided by c squared equals 1. The representation in 3D is for the hyperbola of one sheet, you have something like, you have hyperbolas, so well, at the end would look something like this. All this, you notice that is hyperbolas. So this is the hyperbola of one sheet. We have a separate video on this, and the hyperbola of two sheets is something like this here, and you have the axis here. So both of these converge or are asymptotic to this elliptic cone. The same way as the so here hyperboloids are asymptotic to elliptic cone. This is the same way as the hyperbola in the xy plane, that is square a square x divided by square a plus minus square y divided by b squared equals 1. The same way as this hyperbola is asymptotic to the line x squared divided by a squared minus y squared divided by b squared equals 0, because when you equalize this to 0, that is, instead of putting 1 you have 0, then you can send the y this side and you will have just a linear equation, and so you have lines. So the same way as hyperbolas, when you replace this one asymptotic to lines, these hyperboloids are asymptotic to the elliptic cone. For example, here, instead of having this one, if you put 0, this would pass and you will have square x divided by square I plus square y divided by square b equals square c divided by c squared, that is exactly this. Also here, if you replace this one with 0, well, here with 0, then you can pass this 2 there and you have square c divided by square c equals x squared divided by a squared plus y squared divided by b squared, and so you have again a elliptic cone.